Welcome back. It's week number 5. Is that right? I think it is. So we are more than halfway done now. And, well, I don't know. That could be a good thing, or suppose it depends on your perspective. But yeah, we have now had week 4 where we looked at the advection equation during the lesson. And we also then had the exercise where we were dealing with the advection diffusion equation. Once again, I would say if you have any comments about how things went in week 4, it would be handy for you to put them in here at the poll link. I'll put it once again to the spot in the Zoom chat. And yeah, I think in particular, I'd like to know about how things went with the exercise, because it was a new exercise. And it's always nice to know whether it was reasonable, whether it was too long, too short, too difficult, or too easy, or whatever. So any thoughts you have about the exercise would be most helpful to me. And otherwise, yeah, I suspect that the lecture material itself probably wasn't too much of an issue. But I'm more interested just to know if you have any comments about how things have gone with the exercise. So please, yeah, feel free to add some comments here at the poll link. This is one of the best ways for me to get some feedback from you. And while I'm buying time here, letting you think about the exercise for a moment, I will say that so far I think 6 people have responded for the midterm feedback. That's pretty good. I think right now there are maybe 7 or so, maybe 8 people in the Zoom. There are 7 right now, so including myself, that would mean that, if all of you happen to have responded, then we have everybody here sharing their feedback on the midterm feedback form. But I did not yet put together the summary of the feedback just because I wasn't sure whether everybody had commented. So I'll say a couple things about the feedback I've received up to this point in the e-form. And if you haven't filled it in yet, please do so in the next couple days. I think it's open maybe until Friday or Wednesday. I don't remember when I had set the deadline. But yeah, I think if you could and haven't done it yet, please fill in the midterm feedback just so I can see how things are going again, on top of the feedback that we get at the start of the lessons. Overall, I think it looks pretty good. I feel better about how things are going this year than the years past, and perhaps that's in part because the course has moved from the bachelor's level to the master's level, and it's no longer a course that is required for the students to take. So I think for the geology bachelor's students at the time, this was something that they maybe didn't look forward to so much as a course, because there was quite a lot of feedback about how difficult it was in the last time when I taught it. And so that's not so much the case this time. Looks like overall people are fairly pleased with how things are going. And, there's a little bit of a variation in terms of how well it's going for different people. Some people, it's going great. Other people are saying, it's going okay, but there's some challenges, of course. And certain exercises, if you get stuck at the beginning, for instance, can be frustrating because you're not sure how to proceed. But it looks like, for the most part, things are fairly positive. The difficulty, and I can share a kind of more detailed summary maybe next time. The difficulty responses were between 5 and 8, which is also about what I would hope to see. So I don't want to see it that it's too easy. I also don't want to see everyone saying 10, because that's, of course, maybe meaning it's not quite appropriate. And the amount of work, on average, people are somewhere in the 6 to 8 hours range. But I'll show you the details about that next time when we get together, just in case there's a couple additional responses. But thanks very much so far for those who have responded with the midterm feedback form. Very helpful indeed. And there are now a few comments here about the exercise as well. Not too hard. Liked it. Exercise was quite straightforward. I guess that's a good thing. I tried to kind of make it that way because we were dealing with this lovely equation that we had for the transient heat transfer with the advection diffusion equation, you see that even in one dimension with constant material properties and things like that, you end up with a kind of nasty looking equation, and converting that to Python does take maybe a bit of care, but it's a good exercise to go through in a sense that I think it's within your skills to do it, and it seems like people have generally been able to do that from what I've seen, and that's a good thing. And yeah, so I think that's good news about the exercise overall. Yeah, maybe, unless there's any other comments, get to see our points. Yes, very good question. So I have been a little bit behind with getting the kind of grading thing up and running. It's now working for the automated grading, which means that Levi can now set to work on giving you some feedback about the earlier exercises. So I will run the auto grader. I think I can safely do at least exercises 1 through 3 at the moment, and possibly exercise 4 very soon thereafter. So you should see some points pretty in the relatively near future. For those of you who have not taken the GeoPython course, I'll say just a word here about this automated grader. So you've noticed in the notebooks you've been filling in that there are the tests in there, and you basically want to make sure that your code passes the tests in order to know that it works properly. And that's true also for this automated grading system that we use, that we can basically run a little script that will go through, look at your exercise, and check to make sure that all the tests in the exercise that you can see are passed. But we also have some kind of hidden tests that you're not able to see that we can run to make sure that your exercise solutions are in fact correct. Now, what that means is that once I've run the thing, you will see in your GitHub repository, let me see if I can maybe find an example here. Let's go to GitHub. I'll take one from the GeoPython. Boy, I don't know if I have my exercise. Let's see if my exercise 2 got auto-graded. It did. So this is for the GeoPython course, but it will look the same for our course. I just don't have an example handy. But in the GeoPython course, just like in this one, there's a README file that is in each one of the exercises. And what you'll see after the auto-grader has run is there will be this extra piece down here at the bottom of your README file that gets added there. And it says, here's your grade and feedback. This many points out of 10 in this case, because it was a 10-point exercise for the GeoPython course. And this score out of 10 points will be based on the cells in the exercise that can be automatically graded. And so this will be the cells that are things like where you have to make a function, or whether you have to like do some kind of calculation. Those can be automatically graded, but we don't automatically grade the plot cells. So any points that would be granted, for instance, for making a plot will not be included in the score that you would get here. So you might have done everything correct and see that you get like a 14 out of 20 for the score that's assigned by this grader bot. So that's the thing that will happen to give the score the first time when we run the automated grading. And what's happening at that point is we've graded the automatically gradable parts of the exercise, and then Levi will need to manually look over the exercise and assign the points for the plots and things like that. So it's a preliminary score when you see that. And so don't panic if you only got half the points or something like that, because one of two things could happen. One is that there are a bunch of points available in plots that can't be assigned by the automatic grading. It's theoretically possible we could get it to work with the plotting, but it's a pain, so I haven't done it yet. But the other possibility is that your code is actually correct, but for some reason fails one of the tests. And this is also something where, like, when Levi looks it over, he'll check and see whether the code actually does work properly, but maybe doesn't work if you give a Python list instead of a NumPy array or something like that when you use the code. So that doesn't mean you've done something wrong. It just means that the automated grader failed because it didn't, like, the test itself wasn't able to be passed by your code and in fact your code might work properly, in which case then Levy would override what the automated grading had given and give you the full points maybe for that problem. So I hope that makes sense, but the thing to look for will be that in the next week or maybe in the next few days for exercises 1 through 3 at least, probably exercise 4 maybe by the end of the week, you'll start seeing this little extra piece tacked onto your README files in your exercises 1, 3, 4, whatever, 2, whatever, the first 4. And that will give you your preliminary score. And then once Levy has looked it over, he'll replace where it says grader bot with his own name. And then you'll know that that's your kind of final score for that exercise. And then probably there'll also be a few comments at the bottom saying, nice job, and things like that. So yeah, that's the plan as far as the exercise grading goes. The grader bot thing works pretty well, but it's not sort of foolproof, and so occasionally correct answers get flagged as incorrect and things like that. So don't panic again. It's only a kind of first pass at the exercise score. So thanks. Good question about the points. Anything else at this point? Got a few more people here now in the Zoom, so I'll just remind you all that I did not go over the midterm feedback in detail at this point because there's so far 6 responses. If you haven't filled in the midterm feedback, please do that in the next couple days so that we can have a nice representative sample of responses from the course. All right, if there aren't any other urgent questions at the moment, I'm going to go here to the course page. And you will hopefully see on the course page that lesson 5 is now visible and available. And actually, maybe there's one thing I'll point out before I go to lesson 5, and that is that there's been a slight change in the schedule here for the lessons. So lesson 5 originally was going to be building a numerical model. That's going to come next week. So I've bumped that one down. And this week we will talk about the viscous flow equations. I think earlier I had suggested I might take this out of the course, if you happen to remember that. And I ultimately ended up deciding to leave it in because there are a few interesting things in the exercise this week that I think are useful skills to practice. And so we'll move our building a numerical model to next week, and that should hopefully then put us in a good position for the final week to be about quantitative thermochronology. So yeah, that's a little preview of where we're headed today, because we're going to talk about viscous flow just a little bit. There's kind of like last couple weeks, there'll be a sort of short introduction, and then you'll be able to get started on the exercise, and I can be here to answer questions if you have them when getting started. So we'll have a little lecture about rocks and ice as viscous materials. And then there's some notes here about viscous flow down an incline, as well as an article that relates to the lecture slides. Both of these things are kind of optional. If you want to look over them at your own pace, you can. Then there's some theory that will be used in exercise 5 that we'll take a look at just briefly, but you'll refer back to it when you're doing the exercise itself. And then of course there's exercise 5 linked here. So we're going to start out with our discussion about rocks and ice as viscous materials. I'll go here and put the slides up so that you can hopefully see my screen. I think that should be the case. And yeah, I think we can just jump right into this. So the topic is basically about how we can use viscous flow laws to describe the deformation of rocks and ice and other fluids. That basically anything that behaves as a fluid can be described in terms of its deformation this way. So we'll introduce some basic relationships for viscous flow of rock and ice. Then we'll look at some different end member types of viscous flow in a channel. This will be related to the topic for the exercise this week in some sense. So it's worthwhile to just go over these kind of end member behaviors of fluid flowing within a channel. And then we'll talk about some of the effects that make viscosity, the kind of property about the fluid's resistance to flow, nonlinear. So effects where there's a temperature contribution or other things that affect the way in which the fluid is flowing. So yeah, that's where we're headed. And again, this will be sort of a short introduction that'll lead us into the exercise. So if we look here at an example of viscous flow of geological materials, there are plenty of them around us. And we could consider, for instance, a very nice one being the flow of glaciers as they move down a valley. And that'll be the focus of the exercise for this week. But essentially, the weight of this ice is sufficient to drive it to flow downhill under its own weight. Once the ice thickness gets thick enough, it essentially begins to deform internally and it flows just like a very slowly flowing fluid. And this is something that we can actually monitor reasonably well with various measurement methods to allow us to understand how quickly ice might be flowing in a glacial valley, for example. And again, this is basically just the fluid is heavy. In this case, the fluid is ice and its weight plus some slope, which often is the case when you have some ice forming up at a higher elevation and flowing downhill, causes it to flow just like this example from Alaska. Another example related to ice, but a little bit different, is glacial isostatic adjustment. So I presume that you're all at least somewhat familiar with the idea that if you have some landscape here in a very geophysicist view of what happens, here's some landscape before glaciation. You put an ice sheet on top of it. The weight of the ice causes the surface of the earth to subside beneath this thick pile of ice. And after some period later, when the ice age is ending, the ice melts and you're left with a surface that has been depressed from the weight of this ice. And then, of course, over time, that surface will gradually move back up into its isostatic equilibrium. And that equilibrium elevation would be, in some cases, several hundred meters different from where it was in the glacial period. And this is something that's familiar perhaps to us because, for instance, as shown in the map here of Northern Europe and the Nordic countries that are our neighbors here, these are rates of the post-glacial uplift of the land surface that were measured, I don't know over what time scale in this case, but this is an article from about 10 years ago in the Helsinki Sanomat, where you can see, for instance, in the Gulf of Bothnia, uplift rates of around 8 millimeters per year of post-glacial uplift of that landscape. And that's a relatively rapid uplift rate for considering a geological process. This uplift, and the reason it's connected to viscous flow, is essentially governed by the viscosity of the uppermost part of the fluid part of the mantle, the asthenosphere. So the ability of this surface to uplift, it would like to, for instance, restore to this fully rebounded geometry as soon as possible, but it's being slowed by the rate at which the uppermost mantle, the asthenospheric part of the mantle, is able to flow. So that's our connection to flow in that case. And of course, we could find other examples if we wanted to. If we start with our kind of simplest question here, if we're going to talk about viscous flow, we have to define first off what is a fluid. That's the material that will be deforming. And in this case, we'll give a generic definition that this is any material that flows in response to an applied stress. So what you consider a fluid may in some cases depend on the time scale at which you're looking at the deformation of the material. And we can think of fluids that we know every day, water and honey, oil, other kinds of things like that. But of course, if we look at longer timescales, we can also see things like ice that will behave in a fluid manner, and even the interior of the Earth will deform like a fluid does over long timescales. The deformation in the case of a fluid is continuous, so there are no kind of discrete slip surfaces or things like that, but rather it's just continuous deformation within the fluid. And the stress that you experience in the fluid will be proportional to the rate at which it is strained. So this is part of the definition of what we can consider a fluid, that the stress, in this case, shear stress, is indicated by the Greek letter tau, being proportional to du dz, which would be a one-dimensional velocity gradient, where u would be the velocity, z would be the spatial coordinate in this case. So that's our basic definition with the proportionality in here. And since you can see this proportionality symbol here, you can imagine that we're going to replace that with a constant in the next slide. And sure enough, that's what we have here. So the constant that relates this stress to the rate of deformation, the strain rate, is called the viscosity, or dynamic viscosity, but often people just call this the viscosity, indicated by the Greek letter eta, although you'll see also the Greek letter mu used sometimes. It depends a little bit on the field. There's probably also other letters that are used there, but we'll use eta just because that's what I think is used most frequently for my kind of community. And the units it has here are Pascal seconds, so it's maybe not the most familiar unit to you, but we'll look at some values of viscosity in a couple slides, and that'll hopefully help give you some idea of what the viscosity value means. But basically, in terms of the concept, you can think about it as a resistance to flow. So the larger the viscosity is, the more resistant it is to flowing. So low viscosity will flow easily, high viscosity will flow less easily. There's a nice little animation here we can click on over on the left side of the slide to give you some kind of idea. So here we have something like water being poured from a pitcher or something like that, and you can see it kind of sloshing around and flowing easily. And then here's an example of like softies or I don't know, toothpaste or something like that with a higher viscosity that, yes, it still behaves physically in a similar way, but the rate of deformation within the fluid is much slower. And so while this water kind of sloshes and very quickly forms almost a kind of flat surface, you can see that this other fluid is still kind of slowly oozing into its final position. And ultimately, over a long time, the two would come to a maybe similar resting position, but they're deforming at different rates. And just for the sake of completeness, there are also other viscosities that you might come across. So you may have heard of a bulk viscosity, which is often referred to as compressibility. That's another material property, but it's not the same thing as the dynamic viscosity. Kinematic viscosity is another one. They're similar, but not the same as the dynamic viscosity. So just be aware that when you talk about viscosity, most of the time people will just say viscosity and they mean dynamic viscosity, but there are others as well. So just to give us maybe some benchmarks, some kind of points of comparison, we can think of fluids that we're familiar with already and what their viscosities could be. So probably one of the more familiar fluids you encounter in your daily life is water. It has a viscosity of 10 to the minus 3 Pascal seconds. If we treat air as a fluid, its viscosity is around 10 to the minus 5, so 2 orders of magnitude difference there. And you can kind of feel that if you move your hands back and forth like I'm doing right now through the air, very little resistance. Even in my sort of COVID weakened body, but not to say I have COVID, but that I just don't do any exercise anymore, so I'm not strong. I can move my hands back and forth in the air and there's very little resistance. If I did the same thing in water, I would feel that a little bit more. It would require more effort and more energy for me to move my hands through water. And you could imagine if I somehow immersed myself in honey, that it would be even that much more difficult to kind of do the same thing. That's because the stress that is needed to deform at the same rate would be larger in that case because of the higher viscosity. If we continue on down the list to some other examples of different fluid viscosities that are a bit more geological, we have basaltic lava at 10 to the minus 3. And if you've ever seen lava flows from basaltic volcanoes, you see them flowing relatively easily. And that's because their viscosity is fairly low. And if we go to something like ice and on up the list, the viscosities are getting higher and higher, covering about maybe something like 20 orders of magnitude difference between basaltic lava and granite, and this could even be perhaps a little bit of a low number for granite. It could be 10 to the 21 or 10 to the 22 even, depending on the temperature. So very highly variable numbers here for viscosity of different materials. Rock salt, which we view as geologically a relatively easily deformed fluid, has a viscosity of around 10 to the 17 or 10 to the 18 Pascal seconds. So if you have a chunk of rock salt sitting on your table, one of those nice Himalayan salt lamps or something like that, it's not like you're going to watch it ooze onto the tabletop, but it's staying there relatively coherently. But over millions of years, eventually you would see that kind of oozing taking place also to the rock salt. Now, when we talk about viscosity, there's a couple different classifications we can use to describe it. You'll have these lecture slides to look over, so I'll go over this a little bit quickly, focusing mostly on the things that we need to know for the exercise. But the example that we've seen so far, where here is our stress being equal to viscosity times the strain rate, that applies to a Newtonian material, which means there's a linear relationship between the shear stress, tau in this case, and the strain rate, du dz. So in other words, there's no kind of exponential or anything. Tau is directly proportional to the strain rate. In other words, what we have here is a viscosity with a constant value that doesn't depend on the strain rate, doesn't depend on the flow velocity, and that's not always the case for other materials. For some examples, air, water, motor oil, or thin motor oil at least, are practically Newtonian in terms of how they deform. Rock salt is often treated as Newtonian in geodynamic models, for example. So there are some materials that are close to Newtonian, but basically rocks, for the most part, won't deform as Newtonian fluids, and that's something for us to be aware of. Same thing applies to ice, actually. And that's perhaps why that's relevant to us. But with our linear viscous fluids, we can take a look at a couple different examples here of the expected behavior of a linear viscous fluid. We'll just explore this first before we go into the example of nonlinear viscous fluids. And this example that we'll look at here just briefly is for a fluid that is trapped within a channel. So here we have a kind of cross-section through some channel of, let's say, infinite width. So in and out of the screen, this extends infinitely. Where we have a top side to the channel, this would be like some kind of wall or barrier on the top, and a bottom side to the channel as well. And then within these two walls is our fluid. And this can, like the sort of fluid behavior for what's called laminar flow, so not turbulent, but laminar flow, which is kind of well-organized flow in the same direction, generally applies to highly viscous things. That deformation, or the expected velocity for a fluid in the channel, can be calculated using this equation here. If you have happened to have taken my geodynamics course, you will have seen this equation before, but if not, don't worry about its origin so much as just the fact that we can consider how a fluid will flow as a function of, here, dp dx is a pressure gradient. So this is a difference in pressure on one side and the other side of this channel. And then here is this u naught term. That's the velocity of the top wall of our channel in this example. So those two things will drive our fluid to flow. And we have boundary conditions here that at the bottom of the fluid channel, at z equals h, the velocity has to be 0, which means the fluid sticks to the channel wall. And at the top of the fluid, or the top wall of our channel, the velocity is u equals u naught. And that's at this location here, which again means the channel is such that the fluid basically sticks to the wall. In the simplest case we can consider here is a Couette flow. What is happening in this case is where our pressure gradient is 0. So pressure here and pressure here on either side of the channel is equal. And our top wall is moving at some velocity. So u naught is not equal to 0. What happens in this case basically is that the top wall of the channel moves and the fluid shears within it such that the velocity would increase from 0 at the bottom up to its maximum of u naught at the top of the channel. So this is just a linear increase in our velocity for a Couette type flow. Geologically, this could occur in a few different examples. Actually, the article that's linked on the course page by Gemmer et al. In 2004, a little bit of an older article, but very nicely shows some of these kind of different fluid flow behaviors in a channel. In their example, this Couette flow would occur when you have a layer of salt with a detached sedimentary layer on top of it. So this is something where like there's an extensional fault that's pushing the top part of the channel to move to the left in this case, and the fluid is being dragged along with it. Solution looks like this. It doesn't really matter so much other than what you see here in the end. If you put in dp dx equals 0, is that some terms drop out and you're left over with something that looks like this here, where you have u0 times 1 minus z over h. So if z is equal to 0, you get u0, because this term goes to 0. 1 times u0 is u0. So that's how you get your velocity of 1, or u0 at the top. And at z equals h, this becomes 1 minus 1. And this whole term goes to 0, which is how you get your velocity of 0 at the bottom. So that's our one example. The other case is Poiseuille flow, and this is occurring in a case that the top boundary of the channel is fixed in place. So u0 equals 0, but now we have a pressure gradient such that there's a higher pressure on one end of the fluid and a lower pressure on the other end, and that causes a velocity pattern that looks like this, kind of parabola shaped velocity, where it's 0 at the top, 0 at the bottom, and increases to a maximum in the middle of the fluid. This will be similar to what we're going to see in terms of a velocity pattern for ice flowing down a channel. So if this was looking down from a sort of helicopter view onto the top of a glacier, where this is one valley wall and that's the other valley wall, and downslope is off to the left, you might see a velocity pattern that looks like this. And again, the solution here is relatively easy to come up with. You basically plug in a 0 here and here, those terms drop off, and you're left with this thing that, as you can see, has this z squared term in it, and that's where you get your parabolic shape for your velocity pattern. So we won't directly use this equation in the exercise, but it's just nice to sort of see where some of these velocities come from, I think, in considering the exercise. So as I mentioned, there's this example of salt tectonics, where you have deformation of rock in relation to layers of salt. And this is something that can be considered in many different parts of the world, particularly well explored in kind of oil and gas provinces, because salt makes a pretty nice cap, and oil and gas doesn't really flow through salt layers very nicely, so it can be easily trapped against a salt diapir, for example. So this is kind of like a plume of salt rising up as a result of the pressure of the rocks on top of it. And if you're interested, the page or the article that's linked from the course page talks about some examples of salt tectonics and how these different channel flows relate to how salt is deforming. Okay, so we've got a couple other things to cover with our introductory material for today, and then we can get into taking a look at the exercise. But yeah, this kind of behavior of viscosity as a constant is not that common. And if we look at rocks, there's a couple things that are pretty important in considering the viscous behavior of rock. One of them is temperature. So what we see is that temperature in rock, viscosity in rock is strongly temperature dependent, such that this viscosity eta is equal to some constant here about the material properties. This is kind of a material viscosity constant, times e to the q over RT. And I guess probably this e to the q over RT thing looks somewhat familiar from the examples we were looking at when we were dealing with Dodson's equations and the diffusion constant, because the diffusion constant also has an exponential dependence on temperature. What we can see here in this case is that e to the q over RT would suggest that As temperature goes up, this term should go down, meaning the viscosity will get lower as the temperature gets higher. And that's indeed what we see. And that's in contrast to the diffusion constant, where the equation would look somewhat similar to this, but there's a negative sign here such that when the temperature gets higher, the diffusion constant also gets higher. So just be aware that this sort of temperature dependence is somewhat like that for diffusion problems, but again, there's a difference in the sign between these two equations, so that you end up with the viscosity going down as temperature goes up. So if we look at the viscous strength of rock, for example, here this is shown as like a kind of view into the earth, so down is going to increased temperature. This sigma d would be a differential stress, so that's essentially a measure of how strong the rock is, and you can see there's an exponential decrease in the rock strength as you go to higher temperatures. So that is that's where that kind of idea comes into play. I'm going to skip this question. Now, the temperature dependence is only one part of the story in terms of this nonlinear behavior, and that is because there's also something to do with the rocks and how they behave themselves when deformed. And that is that instead of having this shear stress over here on the left side being equal to viscosity times some strain rate, what we often see in rocks is that the shear stress raised to some power n is equal to a viscosity constant times the strain rate. What that means is that when you increase the rate of deformation, for example, by a factor of 2, the stress would go up by a factor of 8, for example. Or in other words, in order to double the rate at which you're deforming the material, you would need to increase this not only by a factor of 2, but by a factor of 2 to the n, where n is often somewhere between 2 and 4. So if n was 3, 2 to the 3 would give you 8 times as much stress needed to double the rate at which the material, the rock in that case, is being deformed. And this has to do with the way in which the rocks are deforming at the crystal scale. And we don't need to get into the details about that here, but just know that there is a nonlinear effect, and this also applies to ice. So we will see this kind of power law behavior when we start talking about ice deformation, and that refers to the fact that you have stress to some power n in this stress and strain rate relationship. So just a super short couple slides about how glaciers are flowing. Essentially, if we simplify our glacier down to a kind of cartoon diagram like this, we've got a zone of accumulation up at high elevation. That's where the snow is falling. Zone of ablation down at low elevations where the snow and the ice are melting. And what happens to the snow as it's accumulating and incorporated into the glacier is that it's basically flowing down somewhat parallel to the surface of the bedrock over which it flows, from the accumulation zone to the zone of ablation. Now, our glaciers can, in this kind of cartoon diagram, we can treat them in one of two ways. One is that they're cold-based and frozen to the bedrock, and so the fluid flow, the ice flow within the glacier is such that the velocity at the bottom goes to 0. Or they can also be sliding along the ice, or sliding along the bedrock, and the kind of mess of stuff, sediment and whatever underneath the glacier can be sliding along that layer at some velocity, which we would call a warm-based glacier, and probably you've already heard those terms before. And that'll make some difference in terms of calculating a velocity profile in the ice, which is what we'll be doing in the exercise. So whether we assume it's frozen to the bedrock, at which case the velocity is 0 at the bottom of the ice, or sliding along, in which case it's not 0, that will make some difference to the velocity profiles that we calculate. How do the glaciers move? Well, two ways. We mentioned basal sliding already, so this is sliding along on the substrate. And, this can occur a number of different ways. Doesn't really matter too much for our purposes today, but that's one way in which the ice is moving. But of course, it's also deforming internally, and in which case, this is sort of like a nonlinear viscous behavior. that is sensitive to temperature. We won't worry about the temperature in our calculations today, but in the exercise at least. But it is something that still is sensitive to temperature. And the deformation is concentrated near the bed or close to the margins of the ice. That's where it's deforming most. And that kind of takes us in the direction of the exercise, in which case today what we'll be doing is essentially looking at how ice flows down a channel as a viscous fluid in two different examples. So we'll look at a velocity profile across a glacial valley. So kind of looking from like helicopter view down at the ice, at the pattern of the velocities that go across from one side to another of a glacial valley. And then we'll also look at an example of ice flowing down an incline, which is kind of shown here in this cartoon diagram above, where we have some inclined slope and then a fluid, in this case something like ice, that is flowing down that slope as a result of the weight of the fluid. So just to review quickly, when we talk about viscous flow, we're basically looking at a fluid behavior where the deformation rate is proportional to the stress that's applied to the fluid. And then we looked at these Couette and Poiseuille type flows. So these are end-member flows of a fluid inside a channel, where you can either have a kind of linear increase in the velocity for the Couette type, or for the Poiseuille flow, we have something that's more like a parabolic velocity pattern, where the velocities are zero on either side of the channel and increase parabolically across the channel. And that's driven by a pressure gradient, in contrast to Couette flow, which is driven by motion of the boundary of the fluid. And then finally, what we saw was that most rocks don't exhibit this linear relationship between stress and strain, but they're nonlinear, which can be a function of temperature, but it's also a function of the material properties themselves and how rocks and ice are deforming, such that in that case, the relationship between stress and strain rate follows a power law instead of being directly proportional. So that's our kind of quick introductory stuff for today. Not all of that is directly related to the exercise, but just kind of giving you some background in case you don't know anything about viscous fluids. And the point here was just to kind of introduce some of the main concepts that we would need for today's exercise. What I'm going to do now is maybe just show you a couple other things, and then perhaps we'll take a short break, like just a kind of 5 minutes break before we introduce before I introduce the exercise. But I'll just show you some of the other things that are in the lesson for today, and then we can take a quick break and come back and take a look at the exercise. So yeah, I mentioned there's this article about salt tectonics. You can have a look at that if you would like. It's should be available at least if you're on the university's network, or you can connect with the VPN to be able to access that. I didn't want to link directly to the PDF, but it's there. The lecture slides are already up on the course page as well. Item number 3 here is about viscous flow down an incline. So if you're interested to see the theory about how fluid flowing down some inclined slope is driven to flow, you can read a little bit here. I won't go through this in any detail, but essentially we can come up with a relationship here that allows us to calculate how the shear stress varies inside the fluid. And once we know how the shear stress varies in the fluid, we can then link that to our viscosity and strain rate and do some rearranging of different terms, such that in the end you can integrate and find a velocity profile for the fluid flowing down a slope. You'll notice this looks a bit like a Poiseuille flow, because essentially what we have, if you look at the pattern here, is like half of a parabola. And so there is definitely a connection there between, this is like kind of half of a fluid flowing down a channel. But yeah, you can find some notes there if you're curious, just to see how that that kind of background math works out. In addition, for your further mathematical enjoyment, we have the theory for exercise number 5, and this is essentially going to look familiar, because here we have again, a channel with fluid flowing in between the two walls of the channel. Some of these equations, in fact, will also look pretty similar. And essentially what's done in this is a derivation of the velocity profile you would expect to see for a linear viscous fluid, which we have actually seen. So this equation here would be the velocity pattern for a Poiseuille flow, in which case the velocity of the channel walls are 0 on both sides, and then we can solve here to get our parabolic velocity pattern. Saw that before. But then the same thing is done here for a case where the strain rate is now, or the shear stress is raised to some power n. So that's for our nonlinear viscous case. And similarly, you're kind of walked through the derivation for how you would get a velocity calculation for a power law or nonlinear viscous fluid flowing down a channel. So you will need some of these equations in the exercise for today. You'll do some kind of rearrangement of some terms in these equations to do some calculations in the exercise. So you can follow the examples that are here to do that. For the second problem, so the first one is kind of can be used for this like velocity going across a glacier from one wall to the other. So kind of plan form, map view velocity. Problem 2 looks at velocity of a fluid flowing down a slope. And actually problem 2 is, I think, actually supposed to be problem 3. Now that I look at it, this is not, I don't think, right, but this is part 2. So yeah, I think I should probably just call that part 2. But same kind of thing. This is the way in which we can calculate what the velocity would be for the fluid flowing down some inclined slope. And then we do the same thing for this power law equivalent relationship, and you come up with a velocity equation that looks like this. So you'll want to look through some of this as you work on the exercise for today. And I think maybe I'll leave it at that for the moment, because I don't really want to go through the equations themselves in detail at the moment. But yeah. Are there any questions at this point? Getting a little bit of background squawking. So I might suggest we take a 5-minute break here, and I'll go see what these birds we're watching are up to, and then we can come back in 5 minutes or so at let's say 10 after 3. We'll come back and we can take a look at exercise 5, and then there should be some time for you to get started on exercise 5, and I will be here to assist and answer questions. So let's come back in 5 minutes or so, and we'll continue then.